Hi. Good morning, everyone. Let's get started after recording issues. Topic for today, we're going to wrap up BGP and move on to designing IP, and I'll explain what that means in a minute. Just a quick recap of where we are. If you remember, in the context of BGP, we spent the last lecture talking about the high-level goals, the high-level approach, and by and large, we didn't really get into the weeds of how the protocol works at sort of the router level. And so that's what the plan is for today. Quick recap of where we are. All of last lecture, when we talked about inter-domain routing, our model was a topology that looked like the one that's up here, which is what we call the AS graph, or the autonomous system inter-domain graph, where each node in this graph is one autonomous system. And I hope you remember, but just to recap, you should now know how BGP works at the level of this AS graph. Okay, we said destinations are prefixes. Each autonomous system advertises the prefixes it can reach and its path to those prefixes. And each autonomous system listens to those advertisements and selects the routes it wants based on policy. And we talked about these Gao-Rexford rules for what those policies look like. So at the AS level, you now know how BGP works. The main challenge we're going to address today is that, of course, in reality, there is no such physical entity as an AS per se. What we have is a network of routers and links. And so the real challenge is how we implement that BGP AS level policy making when every single router is acting independently. So how do you actually do a distributed implementation of what we've been discussing so far? Okay. And in particular, within this graph, we'd highlighted that you have certain routers that are kind of special in the sense that they are border routers, which means that one of their neighbors is in a different autonomous system. Okay. So wrapping up BGP means the main question we have left to discuss is how do we distribute this BGP process? How do we make sure that all the routers in an AS are actually implementing what we were saying an AS was implementing before? And so sub-questions are, what's the role of border routers versus interior routers? How do we actually integrate the intra-domain routing with this inter-domain routing? So the two finally have to meet together. Okay. And then what are the actual messages, protocol messages that are being exchanged between routers in order to achieve this? So one of the things you'll hear when people talk about BGP is they'll say, these routers speak BGP. This is just BGP-specific language for a certain way of implementing the BGP protocol. What it means is, when we talk about who speaks BGP, we're talking about which routers are advertising these routes, these different prefixes. And the answer is that in BGP, it's the border routers. So the border routers are what we call BGP speakers. Okay? What does it mean to speak BGP? It means you implement the BGP protocol specification. So if you're looking for punishment, the entire BGP protocol spec is out there. You can go read it. It's many hundreds of pages long. I wouldn't recommend it, but it's there if you want to know all the gory detail. So what it means when I say you implement the BGP protocol, it means you have code running at that router that implements that protocol specification. It knows how to send out the messages that are in that specification. It knows how to receive them and what actions to take when you receive those BGP messages. And that's what we're going to talk about today. Okay? So it specifies what messages BGP speakers exchange, both their syntax and their semantics. So what actions you take when you receive these BGP messages. One point to highlight before going forward, I think somebody actually raised this last time. Not all border routers in an autonomous system have to speak BGP or have to actually run BGP. The canonical example, and this is again what helps scaling on the internet, let's say you had a customer that only has one provider. Okay, so the entire autonomous system connects to the internet through one provider. So this is, let's say Berkeley, for example, has one provider. It's AT&T. That's the way Berkeley connects to the internet. In that case, you don't really need to run BGP. And if you go back to Murphy's lectures on default routes and static routes, we're going to use the same trick here. So in that case, what we're going to do is we're going to say that the provider is going to advertise the prefix on behalf of its customer. And the customer is just simply going to have a default route that says, for all addresses not in my autonomous system, just go to my provider. Okay, so what that looks like is this example here. I have a provider and a customer. The customer has been given the prefix 130.132/16. Okay. What the customer is going to do is it's going to configure the routers within its own AS to say, if there's any address that is not 130.132, just send the packet to my provider's network. Okay? That's all you have to do. And in your provider's network, what you're going to do is have a static route that says any destination that is with the prefix 130.132, just send it to my customer. And then the provider is going to play the role of the BGP speaker on behalf of the customer, which means it's going to advertise that prefix to the rest of the internet on behalf of the customer. Okay, so just know that this special case exists. The rest of the lecture, we're not going to worry about this particular case. Any question on these default routes in BGP? Okay, so with that, a second terminology, BGP-specific terminology, is you'll hear this term BGP sessions. What a session is just two neighboring routers that are exchanging BGP messages back and forth. We say that they're engaging in a BGP session. Okay? And so if you look at one of these border routers, they have two types of BGP sessions. One is the session that a border router has with a border router in a different autonomous system, so run by a different operator. We call this an external BGP session, or eBGP session. The second type of session is the exchange of messages that happens between a border router with all the other routers, both border and interior routers, within its own domain, within that AS. We call these internal BGP sessions or iBGP sessions. Okay, so these are iBGP sessions here in red. If your head is starting to hurt, eBGP, iBGP, IGP, I don't blame you. Let's recap them very quickly. eBGP sessions are sessions that a border router has with border routers in a different autonomous system. Okay. This is how you're going to hear about prefixes that are out in the internet, outside of your autonomous system. This is also how you're going to tell the rest of the internet about prefixes in your own autonomous system. iBGP, sessions between a border router and the other routers within its own domain. This is how you're going to take that information you hear from other autonomous systems and you're going to distribute it within your domain. It's a distribution mechanism to share what you've learned from the inter-domain sessions. Okay? And finally, IGP is Interior Gateway Protocol. You've heard this before in Murphy's lectures. This is just the formal term for an intra-domain routing protocol. It's how routing is done within a domain. This is our distance vector, our link state, the protocol names are OSPF, RIP, everything that we heard in Murphy's lectures. So how do all these pieces come together? Yeah, so if I go back to this AS graph now, I have my links with costs on them within my domain. So within my domain, I'm going to run my IGP, distance vector, link state, whatever I want, my IGP protocol. It's going to compute least cost paths. At this point, I have routes to all destinations within my own domain, including to my border routers or to other routers in my domain. Right? Then with eBGP, I'm going to learn about external destination prefixes. And then I'm going to take those those routes that I've learned, and share them with all the routers in my domain. And every border router is going to do this. This might look not very scalable. We'll come back to that in a bit. But at this point, any router anywhere in my domain has all the information it needs to reach any destination on the internet. Okay? So if I take a router, let's say the one that's going on the path labeled 3, the path it's going to follow, if given a destination prefix outside its domain, is it knows from the iBGP session which egress router, what is the border router in its own domain that it has to exit traffic through to reach that prefix. And it knows from its intra-domain routing protocol how to reach that border router. And so it can reach any destination on the internet. Let's make that a little more specific. So in this case, let's say that the domain where R7 is had a prefix a.b/16. It would have told R1 about this through its eBGP session. R1 would have told all the routers, including R2 in this example, about that prefix through its iBGP session. And so now R2 knows that to get to A.B, it has to reach R1. And it in turn knows how to reach R1 because of the intra-domain routing protocol, the IGP. Let me repeat this one more way, different way, and then let's pause and see whether that made sense, because this is really how all the pieces come together, so it should be clear. So every router in an AS has two routing tables. Conceptually, this is how we think about it. One is from IGP, from running an intra-domain protocol. I have a table that tells me what my next hop is to all my internal destinations. From IBGP, what I learned is which border router or which egress router I should use to get to any destination prefix not in my domain. Okay, so that's like my next hop in some sense is my border router in this case. And so now if I'm given a packet, remember the packet has an IP address, and I'm going to try and forward it. If that packet's IP address is within my own domain, then I just have to look up the table that was computed for my IGP. I look up the destination address, I get the next hop router, I send it on. I'm done. If that address, however, was an IP address that's outside of my domain, I'm going to do a two-step lookup. The first thing I'm going to do is I'm going to look at the prefix for that destination address, and I'm going to know which egress or which border router I have to send the packet towards. And then I'm going to take that border router and say, what is my next hop? Using the intra-domain, because the intra-domain protocol told me how to reach all my border routers. Okay. Any questions on this? Yep.
So the border routers don't all necessarily have to have direct links to interior routers. They will have to use IPTX maybe at some point to find the connection.
Yeah, that's a great question. How does the border router reach all the interior routers? It knows how to reach them at the connectivity level because we've run the intra-domain routing protocol. In practice, the implementation BGP actually runs on top of TCP, which we haven't covered yet, but you don't need to know that for now. For now, how do I reach my interior routers? Because my intra-domain protocol built up the paths to them. Any other questions? Okay, is this clear? Anyone want me to repeat it? Okay. So in reality, what I've described to you is one way of configuring how the intra-domain and routing and BGP interact, or how they integrate. In practice, there are a few different ways to configure a domain, and different providers do it slightly differently. The one we've talked about, which is option 1 here, and this is what we're assuming in this class, is that a border router runs IBGP sessions to all the other routers in its domain, both interior and border routers. So if I have n routers in my domain and b border routers, this means I have n times b sessions, IBGP sessions within my domain, which is quite a bit. Depending on the size of your network, this might be a problem. Or if it's not, then this is probably the simplest way to do things. In this class, this is what we assume. Just so you know that there are other ways to configure a domain. Another common one, and I think Murphy touched on this in one lecture, is that a border router will only have IBGP sessions to other border routers, not to interior routers. And then each border router is going to inject that prefix as though it was a directly attached destination address into the IGP. So now you have prefixes being advertised into the IGP. Is that reasonably clear to people? Yep.
So this is then an interior router go to a different border router that then has to forward it to the correct border router?
Yeah, good question. Let me go back to that picture here. So what would this mean? Let's say that this router R1 got A.B, and there's the other border router on the right. Let's call it X. And R1 would have told X, I have a prefix A.B. In this case, this doesn't really work very well, but you could have had R1, let me roll that back. R1 could have just injected A.B as a destination into the IGP protocol itself. So it looks like a destination from the point of view of the IGP protocol. Okay? In this particular case, which is why it gets confusing, let me just say it briefly and then not go any further. R1 could have also told another border router. That border router could have advertised, could have chosen, if it was doing the right thing, chosen not to advertise it as a destination because it doesn't actually have a path. Or it could have advertised a very high cost path going there. But then you'd have to do some additional stuff to make that work. So let's not go there. Okay. The third option, and actually this is probably the most common in the very large-scale providers, is they'll run a separate appliance or device called a route reflector. Think of this as a special server, and the job of that server is it sets up IBGP sessions to all the border routers. So it sucks in all the routes advertised to any border router in its domain. It runs a computation to select paths, and it goes off and programs all the routers in your domain. Okay, this is called a route reflector. No, they exist. In this class, we're just assuming option 1, so make sure that option 1 is clear to you. Any questions? All right. So how is all of this actually implemented in terms of protocol messages and protocol exchanges? So the key here, again, the BGP protocol specification has quite a few message types. In this class, we're going to focus really on what we call a route update. But just again, know that there are many other types. For example, there's a type of message to open a session. There's another type of message called a keep alive, just to say this session is still active, this border router is still up, and so on. The one that we care about is what we call a route update type of message. This is a message that informs a border router either I have a new path to this destination prefix, or I have an update, maybe I've changed some of the path length or the actual path associated with this destination, or sometimes what we call a route withdrawal, which is a border router telling another border router, I no longer have a path to this prefix. Okay. So let's dig a little bit into what route updates look like. At the highest level, route updates are as simple as they get. I have a prefix, and I have a set of what we call attributes associated with that prefix. Okay. So the prefix is exactly what we've been talking about. It's a /16, a /24, whatever you want. It represents a whole bunch of destination hosts aggregated into a prefix. The attributes are a general mechanism that we use to describe or express properties about routes. And as you're going to see, all of the secret sauce, all the smarts of BGP is kind of packed into these attributes. So you can think of them as they describe a route. One way mentally to think about it is it's a set of key-value pairs associated with a route, where the key is a particular attribute type, the value is the value of that attribute. And we're going to use those to implement policy and to do route selection and route export decisions. Again, some attributes are local to an AS, so there are some attributes that will be associated with a prefix or associated with a path that a border router will never share with border routers outside its domain or with any router outside its domain, so they're local. There are also attributes that are propagated in eBGP route advertisements, so there are attributes that will get propagated across the internet. And in general, there are many standardized attributes. We are going to talk about 4 important ones in this class. Okay? So first attribute, something we've discussed already, is this notion of an AS path. So if you remember from the last lecture, we said BGP is a path vector protocol. It actually, when you advertise a prefix, you enumerate the sequence of autonomous systems needed to reach that prefix, and this is how we prevent loops. So AS path is just that vector of ASs that you're traveling to get to that prefix. Okay? It's carried in route advertisements. So what it would look like is something like this. So let's say in this example, I have Princeton, and Princeton is AS88. It has a prefix 128.12, 112/16, and it's connected to AT&T. Okay? So the Princeton and AT&T are going to have an eBGP session between their border routers. And in that session, Princeton is going to advertise, this is my prefix. If I dig into what that advertisement looks like, and we're getting now a little bit into the syntax of these messages, what that message is going to say is, here's my prefix, 128.112, so on, and here is my AS path attribute. And my AS path attribute at this point just says AS88, because that's where the prefix is. That message is going to get propagated through IBGP and so on to this other router on the right, which is still in AT&T's domain. And now AT&T, let's say, is going to advertise that prefix further to Berkeley. If I go look at what that message being advertised between AT&T and Berkeley looks like, again, it has the IP prefix. It's the same prefix, unchanged. Now the AS path attribute says 701888. So you know that your path is you're going to through AT&T and then to Princeton. Okay? So pretty simple. AS path just records the vector of ASs needed to reach that destination prefix. The second attribute, any questions on AS path? It's pretty much doing what we said path vector would do. The second attribute is what we call local preference or local pref. This is actually where GAU-Rexford gets implemented, and all the routing follows money gets reflected in local pref. So the way local pref is used is to choose between different AS paths. Local preference is local to an AS, as the name suggests. It also makes sense because remember we said ASs don't like to publicize their policies about customers versus providers versus peers and so on. So local pref stays within a domain. That means it's carried only in IBGP sessions and IBGP messages. And in general, local preference, the higher the value, the more preferred it is. So it's quite intuitive. Let's go back to our example here. And now in this case, we have Princeton again, AS88 up there. And I've complicated the picture a little bit in that Princeton now reaches AT&T potentially through AS100 or through AS200. Okay, it has a path. So AT&T can reach Princeton either through AS100 or AS200. The way we're going to use local preference is that let's say AT&T prefers using the path through AS100 because maybe 100 is a customer and 200 is a peer. Just to reflect GAU-Rexford. So what AT&T is going to configure its border routers to do is it's going to say at that border router, when you get a prefix advertised by AS100, add to that path, internally when you store that path, add a local pref value of, let's say, 300. The value doesn't matter. I'm just picking it out of nowhere. And so now if you looked at the routing table within that border router, you'd see a path that says something like, for this destination prefix, your AS path is 180, and then followed by 88. And this route has a local pref of 300. You would likewise configure on the other end, you don't like AS200 as much, so you would do the same configuration, but you would say, I'm going to give it a local pref value of 100. Okay, so it's lower preference. And now IBGP is going to share those entries with all the other routers in the domain. And so now what is any router going to do? In order to implement GAU-Rexford, the only thing sort of mechanistically that a router has to do is say, I'm going to pick a path to that prefix. I have two options for how to get to that prefix. I'm going to pick the one with the higher local pref. So I'm going to go through 100. Okay. Any questions on this? Yeah. Yeah, today manually often. So the operator knows what kind of relationships they have with AS100 versus AS200. So they configure their routers to say local pref coming from this AS is 300, coming from that AS is 100, which should cause you some discomfort. Any other questions? Does this fully implement GAU-Rexford? So GAU-Rexford said, customer better than peer. So assuming 100 is a customer and 200 is a peer. What happens if AS100 goes down or it withdraws the route? You'd need to update the table and you'd take out 300, the first entry, but you would use your path going through 200. Right? So it's doing the right thing. It's prioritizing. It's not eliminating routes. How would you actually, I think your question is, how would you actually know to get rid of that route? So this is where a route update that's a withdrawal would come in. So AS100, either you time out the route and then the border router would withdraw it, or AS100 might explicitly withdraw the route. Any other questions? Okay, so let's actually move on to a slightly more complicated case now. And as you'll see, the BGP, conceptually, the approach is simple, and what we're trying to do is very intuitive. Implementing it in a distributed fashion given the realities of how ASs interconnect is where things get a little tricky. So this is the same not the same example as before, because so far we've been assuming there's one link between two ASs. In reality, what is very common is that two autonomous systems, especially large ones, will have connections between them at multiple places. So if you're AT&T and Verizon, you probably have connections between the two networks on the East Coast, in Chicago, on the West Coast, in Europe, in Asia. So you have multiple of these connections between two different ASs. Okay? And so now when you think about going back to this Princeton to Berkeley path, you kind of have two paths, right? Either you can go through something like, let's say, the orange level router path, or you could go through this green path here. So notice this is the same AS level path. I'm going Princeton, Verizon, AT&T, Berkeley. So at the AS level, it's the same path. At the router level, it's a pretty different path, right? In one case, you're switching from AT&T to Verizon on the West Coast, and on the other case, you're switching between them on the East Coast. Which route do you think Verizon would prefer between these two? The California route. So the orange one. Why? Yeah, okay, interesting. That's a valid argument, not the one. So the proposed answer was Verizon would prefer it because you're using your own router. So you're assuming Verizon would like to have control over the part there. In reality, Verizon would like the other way because it uses less of its bandwidth, which is an expensive commodity. Right? So reasonable argument. I was going the other way. So let's say that Verizon likes the green path. Okay. Because in this case, I'm saving my bandwidth. There's another reason. Let's go with that. How would Verizon try to influence the way traffic enters their network? So Verizon is advertising Princeton's prefix to AT&T. And somehow Verizon would like to tell AT&T, hey, I would prefer it if you send me traffic to Princeton over this router that's on the East Coast. Okay? So I need some addition. Nothing in what I've told you so far would work. That we don't have anything in the protocol that would allow Verizon to implement this. And so the third attribute is an attribute that is designed to help autonomous systems influence how traffic enters their network. It's an attribute called MED, or multi-exit discriminator. And we're going to use it when ASs, typically the way it's used when ASs have two or more links between them. And the idea is to try and tell the other autonomous system how close a prefix is to the link over which it's being advertised. Okay, so let's go back to that picture here. We had, in this case, the AS that's announcing the prefix. This is Verizon is advertising Princeton's prefix, and it has these two links over which it's going to advertise it. One on the East Coast, one on the West Coast. The way it's going to use it is, MED as an attribute, is when it advertises the route over the East Coast, it's going to say, and again, the exact values don't matter, it's going to say, here's the prefix, here's the AS path. This advertisement has a MED field of, let's say, 10. Okay. And when it does it on the West Coast, it's going to give it a MED field that's higher, let's say 50. Okay, so if you think of these as costs, like our least cost routing, it's kind of trying to say the link on the East Coast has a lower cost. Does this make sense? And so now AT&T, when it hears it, has the option of saying, Verizon is trying to tell me to use this link here on the East Coast. And saving bandwidth is not the only reason Verizon might do this. Let's say AT&T had, instead of a customer that was Berkeley on the West Coast, let's say it had NYU on the East Coast. Right? If you had no MEDs, the path from NYU to Princeton, you would have no way of knowing whether you should send it over the East Coast link or the West Coast link. But it would make so much more sense to send it over the East Coast link, right? Instead of sending it across the country and then back across the country. So MED is a way you can think of it of kind of extending our notion of least cost routing across domains. Again, it's an attribute, it's a hint. There is no reason AT&T has to adopt it. But if AT&T chooses to listen to what Verizon is telling it through its MED fields, then it will choose the MED path, the path that has the lower MED. Any questions here? Yeah.
So would it just be a consideration of AT&T's part? Because it seems like AT&T would benefit from taking the Med-50 route. Because it doesn't have to have bandwidth for one, why would it take that time?
Yeah, great question. Hold on to that thought for just half a slide more. Same question? Okay. So exactly that question, which path or which route does AT&T prefer? And so Verizon said, I prefer the green route. That's what it did with its med field. But in this case, I think somebody said this already, if you're AT&T, you would prefer the orange route. Right? Again, under the assumption that we're trying to save our own bandwidth. Does this make sense to everyone? So what would AT&T do? Right? Ignoring meds, what would AT&T try and do in order to use the West Coast exit router instead of the East Coast exit router? It's clear to everyone why you want to use AT&T prefers the orange path? Right? Because the green path is consuming AT&T's own bandwidth across the country. So what could AT&T do? Yeah?
make the internal links very high cost?
Right. The suggestion was make the internal links very high cost. The thing to remember is actually AT&T doesn't have to do anything to do that. Right? We already have our intra-domain routing and our intra-domain costs. So if all I did was look at the intra-domain cost, so the IGP cost, and I said I got the same prefix advertised to me from two different routers, and when you're leaving Berkeley here, you look at what is my IGP cost to the exit router on the West Coast versus the IGP cost to the exit router on the East Coast, and you're just going to say, I'm going to pick the exit router that has the lowest IGP cost. This is something called hot potato routing, and everyone does it. So if you send traffic that's leaving the network, they will send it out of their network as soon as possible, unless you pay them. You pay the provider to carry your traffic further. So this is very common in cloud providers. If you, for example, sign up with Azure and you sign up for, you don't sign up for any special treatment in their network, then they will take, when your traffic is leaving Azure servers, they will hot potato your traffic. They will send it out of Azure's network as the first chance they get. If you pay Azure an extra fee, then they will actually carry your traffic across Azure's network until, as far as they can close to the destination. The assumption being that Azure is running a better network than the public internet. So what is IGP cost? Again, IGP costs are local to an AS, right? No one's going to advertise their IGP costs outside of the AS. And all it does is every router, what it does is when you get the same prefix advertised by two different border routers, you pick the border router with the lower IGP cost. Okay, so let's go back to that picture here now. And now I'm adding internal IGP costs to AT&T's network. And again, remember, these costs, private to AT&T. And it's not going to share them with anyone else on the internet. And now we're going to say that if you were this router over here, the orange one trying to get to Verizon's network, you would route through the border router on what was the East Coast in our earlier picture. If you were somewhere in the middle, you would just pick whichever one was the lower IGP cost. In this case, happened to be the one on the West Coast, or the one on the right. Yeah?
Why do the ND fields if, for example, if AT&T sends it back up to the left router, what choice does Verizon have accepted? Just accept it.
Yeah, so that was exactly the next point. So hold on, let's come back to see if you still have the question when we're done with this. So if you're looking at this, you should be thinking, wait a minute, this IGP cost is sending me in a different direction from what the med attribute was trying to say, right? So Verizon was using med to say, come in on the left router, not the right. AT&T is saying, I'm sending my traffic out on the left, not the right, because it's the shortest path. So IGP can conflict with med. This is not uncommon. This happens. And so, going back to that example we had, where Verizon was saying a med of 10 for the left and 50 for the right, well, in this case, AT&T is just not respecting the med. Is there a problem with this necessarily? Anyone think it's a problem? Yeah, so there might be some contractual back-end bickering, but it does, nothing breaks in your route, yeah.
What I was trying to say is, isn't it a problem for AT&T, but there is no problem for Verizon because it takes more of their bandwidth?
Right, so Verizon can turn around and do the same. So in fact, this happens all the time on the internet. So for example, if you see two providers A and B and you're looking at traffic going between the east and west coast, what is quite common, for example, traffic going from B to a destination in San Francisco, B would immediately hot potato the traffic and send it over A's network. But the return traffic coming back from the destination to the source, A is also going to hot potato it and send it over B's network. Right, so everyone plays the same game. The point to notice here is that you have asymmetric paths. Right? Your path from a source to a destination may not be the same as the path back from the destination to the source. This doesn't necessarily cause a problem, but it does tell us why asymmetry on the internet is common. And it happens, by design, not necessarily as an accident. Yeah.
So if we're doing hot potato all the time, can't say that we cause a loop or like you just send it back to the...
So this is why I was asking, is there actually a problem? Like, could you get into a loop? How would you get into a loop? So the reason you wouldn't in this case, so let's take the green, right? You're going the traffic going from the source to the destination San Francisco. For A to send it back, the destination would have to be in B, which is not the case here. So you're still following an advertised path to the destination. So you're not going to have loops. So there might be some unhappiness between providers, and they might, get on the phone and talk to each other about it and massage their policies, but it's not causing your packets to be dropped or to loop. Any questions? Yep.
If all the ASs are doing IGP internally, what is the point of NGP? Except for traffic.
Great question. So you might ask, why bother with MED? Anyone know the answer? So what would have happened if the green source here was in LA, let's say? Still in B's network, but in LA. So on the West Coast. Would B have wanted to respect the MED field? So let's step through that. So the green source is on the West Coast. A has told B that it can reach the San Francisco destination. It's advertised that path over their link on the East Coast and their link on the West Coast. If I had no MED, B has no idea where the destination is relative to the East Coast or the West Coast. Right? So it would have no indicator for which one is the shorter path. In this case, it at least knows that, okay, the path on the left is actually the shortest path to the destination. So it's going to use the link on the left. Let me give you maybe a better example. Let's say that the green dot was in Ohio, in the middle of B's network. So going to the left or to the right, to the east or the west, is similar from B's perspective in terms of how much bandwidth it's going to consume. In that case, which way would it want to go? It would want to take the link that's closer to the destination because it's a shorter path for its own customers. Right? So the MED is a useful indicator when there is no conflict between MED and IGP. Great question. Okay, so closing the loop, when our last lecture, we talked about how the typical selection policy, when you receive an advertisement, how do you select which path you want to use? And we said that the policies tend to be you want to make or save money. If they're equal in terms of making or saving money, you want to maximize performance, means take the shortest path. And then you want to minimize use of your network bandwidth. So you want to save network bandwidth to the extent that you can. You should now know, kind of in terms of mechanisms, how this is implemented. Make or save money is your local pref value. This is how we do Gao Rexford. Okay. Maximize performance, that's the length of your AS path. And minimize use of your network bandwidth, that's this dance we play between MED and hot potato. Okay. So now when you think about how BGP is implemented, it should be very clear to you. This is kind of the table for how we apply attributes in a route update. Right? So how is BGP implemented? I get route updates. It has a prefix and a set of attributes. I follow the rules in this priority order that are in this table to decide which routes I'm picking. And everything we talked about, routing follows money. I want to have a good balance of performance. I want to save my bandwidth. All of that follows from applying these rules. And this is a priority order. That's the important thing to remember. I always first do local pref, because that's about making or saving money. And then I try to optimize performance and save bandwidth. Any questions? Right. So BGP clear? Okay. So let's talk about some limitations of BGP at this point. You've seen enough of BGP. What do you think? What are things that you think would work well in BGP or not work well? Where do you see potential problems in the protocol? I had 4 categories. Yeah?
It seems like an additional layer of work we have to do on top of IGP. You also have to handle the external connections. Maybe if you have a lot of different exterior routers, then that becomes more complexity.
Is complexity? Can I summarize this? Yeah, okay, we'll dig into that. Anything else? A broader view, beyond, yep. Right. Human costs, I'm going to lump that in with, I think you're taking complexity to the fact that there's all this manual tuning. Maybe any other? What about security? I had 4 classes. How do people, thoughts on security? How could you imagine misusing BGP? Yeah?
A lot of entry and exit points, so more, I guess, that you have to secure against attack.
Points of entry that you have to secure, that's fair enough. More basic than that. Yeah. Right. So this is like a deeply problematic part of BGP. An AS sends an advertisement to you saying, I have this prefix and here's my path to the prefix. There is no mechanism in BGP to check that you actually have the right to advertise that prefix, that is actually a valid path to that prefix. There's just nothing in the protocol that is designed to catch that. Okay. There's also no guarantee that you say, maybe so you could lie about a prefix, completely spoof a prefix. You could also lie about the path. You could say, or choose to not lie about the path in the sense that you advertised a valid path to a prefix. Then when you got data packets, you just send them over a different path. You didn't actually respect the path that you advertised. So it's really just, this is an indication of how the internet was designed in a pre-attack, pre-security concerns era. The fact that there is just no validation or security checks around BGP. What would happen if an AS said, this is my prefix, I have this fantastic path to a prefix? If I just followed the BGP protocol spec. Yeah. Everyone just sends traffic to that prefix. So we call this prefix hijacking. Right? An autonomous system can claim to be any prefix it wants. So as you can imagine, in the real world, there are a lot of policies. Operators configure a lot of checks in order to make sure, is it strange that suddenly Google is being advertised only from Australia? There are all these sanity checks that go on to make sure these prefixes are valid. There are also protocol standards people are working on that would have cryptographic security around advertisements, so you can prove that you own this prefix, and you can prove that an advertisement traveled across a set of AS paths. But deploying them and getting all of that PKI infrastructure around it has been slow. So securing BGP is still a major issue on the internet, and it's a craft, not a science. We survive because the people who are configuring BGP know their job. What would you do to make sure that an AS actually follows the path that's being advertised? Because you can imagine, using digital signatures or cryptography to make sure that a prefix, you cannot hijack a prefix. What about making sure that a packet actually follows the path?
You send a packet onto a tracer and see if it follows the road that the AS advertised.
Right, so you could send a packet, you can't quite trace the path that packet took. You could use tools like traceroute to see what paths the packet follows, but it's actually a really hard problem and an unsolved problem to make sure that a packet followed the path that you thought it was going to follow. I would say that's a pretty open problem. So you could put a path that you want the packet to follow and hope, but if you have a malicious AS that's not following it, the fact that you said what path you want followed is... so every hop along the way would have to do that. Yes, that would work. Any other thoughts or concerns around BGP security? Okay, so the short answer is that BGP security is a bit of a mess, and that's why people are very, very careful in who and how their BGP policies and advertisements are configured. Performance, thoughts on performance. So I have a hint here in saying that they're performance non-issues, but can you see a concern around performance with BGP? And so performance here tends to be short paths. Yeah? Non-optimal, I would go beyond what you said and say that in general, policy-based route selection is not about picking short paths, right? It's about enforcing policy. So the path you picked based on policy need not be the shortest path. So I said this was a non-issue because this is not by accident. This is by design. Operators are choosing to prioritize policy over path. The other aspect, though, is that your AS path length can be misleading. So if I say I have a one-hop AS path length, there's nothing in BGP or no easy way that allows me to distinguish between that was one AS hop that involved two routers, both in California, versus one AS hop that involved 20 routers spread across the globe. Right? That detail is actually hidden because we are abstracting all that into an AS path. Again, this is by design. ISPs and ASs don't want to reveal their internal topology, but it does have this implication for performance. Prone to misconfiguration, someone brought this up. We have many attributes. The configuration is often manual and ad hoc. Again, configuring BGP, there's a relatively small number of people who are trusted at large operators to actually configure BGP. Anytime there's a configuration change, it's done very carefully, it's tested, it's vetted, and we still have major issues. So BGP misconfiguration is probably the root cause of outages on the internet. And if you Google some of the famous BGP outages, it's quite entertaining. So the examples like Pakistan wanted to censor YouTube, and so they wanted to put in configuration that would filter out routes advertising YouTube. And they got it wrong, and so by mistake they started advertising YouTube to the rest of the internet. And so all YouTube traffic went into Pakistan, exactly the opposite effect. Russia, I think, had a similar thing with Twitter recently. Somebody did prefix hijacking to hijack all the traffic going to one of these crypto companies and managed to actually steal millions of dollars doing that. So BGP hijacks and some of them are malicious. A very large number of them are actually just unfortunate misconfigurations. Okay. And finally, reachability and convergence. I touched on this last time. If you follow GAU-Rexford, good things happen. If you don't follow GAU-Rexford, all bets are off. There's no guarantee even that all destinations would be reachable or that you'd have convergence. And in section, you're going to see this very fun example of how, if you don't follow GAU-Rexford, you could have continuous oscillations in which path you're selecting. So routing actually never converges. Okay, so with that, any questions? Okay, let's take a 1-minute break. We are kind of done with BGP at this point. So any last questions on BGP? Yeah. Yeah. let's keep going. So, rest of today's lecture, I just want to take stock of where we are in the overall syllabus in some sense. We started with this overview of how the internet works, top down, bottom up, and then we jumped straight into L3, or the network layer, which is arguably the most important layer on the internet. And we spent many weeks doing routing. We've done intra-domain, inter-domain, we've done addressing. So at this point, addressing and routing, which I would say is the control plane for the network layer. I hope you got that we're fairly complete on that front. Where we're going to do this week is go back to the L3 or the network layer data plane. Okay? So today's lecture, we're going to talk about what the IP data packets actually look like, and specifically what the IP header looks like. And then next lecture, we have a guest lecturer from Google who's going to teach us about IP routers, how they're built, how they function. And we're kind of really lucky to have him because he is the person that represents Google to all router vendors, so he really knows what he's talking about. And he also defined some of the main router management and router configuration protocols that are in use everywhere today. So OpenConfig, if you Google it, you will find Rob's name. So today let's talk about designing the IP header. Okay? And designing the IP header, if you remember going back to one of our earliest lectures, we said we have packets, they have headers and payloads. We tend to not worry so much about the payload because, especially at the network layer, routers are not looking at the payload. But the header is where all the action is, and so that's what we're going to be focused on. So we're going to talk about the syntax, like what fields and how many bits for the IP header. I know that sounds very boring. We'll try to make it not so boring. But more importantly, the semantics. Why do we have those fields? What do we use them for? And so on. Just a quick recap to get your head back in the right place. Remember, we had talked about layering. So keep in mind where L3 and L3 headers fit between L4 and L2, and how we talked about encapsulating packets in headers and then removing headers when you reach the destination. Okay? Also remember, we had this complicated end-to-end protocol diagram. The thing to remember here is the fact that the IP header or IP portion of the packet is relevant both at routers and at end hosts. It really is the end-to-end interface or language. Okay. Any questions or reminders on the IP header in terms of its role at that high level? No. Okay. So designing the IP header. When you think about designing the IP header, the way to think about it really is not so differently from how you would think about designing an interface. Right? Anytime you have to build a system, you kind of start by thinking about the interface. So think of the IP header as the interface between the source and the destination end system, but also the interface between the source and the network routers. Right? So it would not be an exaggeration to say that the IP header is the interface to the internet. It's kind of a cool interface to design. So when you design it, anytime we talk about designing something, first thing you should ask yourself is, what's the goal? Right? So in this context, what task am I trying to accomplish? And this, again, should be no different from when you design an interface for any piece of code you write. Right? Your module has a certain function. Your interface has to pass the parameters and the information so that that module can do its job. It's going to be exactly the same with IP. We're going to say what tasks are we trying to accomplish, and then what information do we need in order to accomplish those tasks. And then your IP header is just simply how we capture that information. Okay. So with that, what are these tasks? And remember, IP headers are relevant at routers, and they're relevant at the destination host. Right? This is the sender communicating both with routers and the destinations. So I'm going to give you one example. The first thing you should do when you receive a packet, you have to be able to parse it. Right? You have to know what kind of packet is this. Is this an IP packet? What fields are there? So parsing the header and the packet is job number one. We're going to have to do this at routers and at the destination. What else? What was the job of IP? How to forward it? Absolutely. That was the primary role of IP, right? So we're going to need information in the header that allows the router to forward the packet. What else do we have to do? So what's a normal path for a packet, right? So we've forwarded it, What happens when it reaches the destination? Get at the payload. Yeah, I'm going to refine that. So it kind of tell the destination what to do with the packet. Right? So I need to be able to parse the packet at both routers and destinations. I need to be able to forward the packet on to its destination. This is a task that the routers have to do. When the packet reaches the destination end host, the destination has to know what to do with it. Because remember, the packet is not really, it's not headed to the destination. It's headed to some application at the destination. So there's something in the packet header that has to allow the destination to figure out how the packet has to be sent next on its journey towards the application. We'll get to that in a minute. And then, for most practical purposes, we're going to need a response going back to the source. And so again, the destination host has to know how to send the packet back to the source. This is a task for routers as well, and we'll get to why that is in a minute. So this is kind of all you would need to do in a well-functioning, pretty bare bones network. Anything else you can think of? Yeah. Yeah. Okay, so I'm going to broadly call that deal with problems along the way, and we'll get into what potential problems you could run into. And also then the ability to specify some kind of special or more advanced processing that we haven't quite gotten into so far, so we'll get into that as well. So these are kind of the tasks, the consolidated list of tasks. This is all the tasks that you need to capture in the IP header, that your IP header has to have all the information needed to accomplish this set of tasks. It's not such a long list, actually. Okay. So let's go through these a little quickly. They're fairly intuitive, I think. To parse a packet, what information would I need in order to know how to parse this packet? Yeah. Size of the payload. Anything else? Size of the header. Yeah. IP version number. Okay, great. Oops. You got all of them. So first, version number for IP. Why is this so important that I have a version number? Yeah, because if you didn't have a version number, you would be stuck with the same header forever, for eternity. Right? So when you had IPv4 and you wanted to go to IPv6, if you needed a different format for the header and you didn't have a version number, good luck. Right? You wouldn't have been able to implement it. So a version number, just like you have versions for API, is critical. Also, where does the header end? This is because, as we'll get to in a minute, the IP header is not a fixed size. So you have to know how many bytes form the header. And then remember we said IP packets are not all the same size. So you also have to know where the packet ends. Okay. In order to deliver the packet to the final destination, what information do you need in the header? We've had this, assumed this throughout. Yeah. Oh, wait, you jumped, but yes. To get to the destination, you need the destination address. To get back to the source, you need the source address. Next task was tell the destination how to handle the packet. And here I want to go back to our protocol diagrams that we had and our different layering architecture that we had earlier. And remember now that when the packet arrives at the destination, it's coming in off the wire and it's traveling up this protocol stack. Okay? So now the packet has reached the destination. It is at the right IP destination. And so in your operating system, you've looked at the IP header and you said, great, I've reached the IP destination. What next? Remember that packet ultimately is being consumed by an application. What do I need? You need one of those, not the second. So I need at least the protocol number, something that identifies which protocol at L4 is going to process this packet. Right, so I received the packet at IP. I need to know, is this a TCP packet, in which case I'll send it to be processed by TCP? Or is it a UDP packet, in which case I would hand it to the UDP module? TCP and UDP we've not covered yet. That's our next topic. These are different layer 4 protocols. But I need to know which one the packet has to be sent to next. Does that make sense? Let me repeat it one more time. It indicates which protocol should handle the packet next. So it's a protocol field. protocols are given a unique number by, again, the numbering agency ICANN or IANA, just like IP addresses and AS numbers. Different protocols will have a well-known protocol value. Okay, and your protocol field is going to carry that protocol value. And this is used at the receiving end to demultiplex where the packet should go next. Question? Yes, so the protocol field is going to be part of the IP header so that the IP layer knows where to send it next. So what does it mean to have a protocol field? So as I said, these protocols have well-known numbers. So for example, TCP is 6, UDP is 17. And so when in my IP header I say my protocol value is 6, what that means is that the next header is a TCP header. Okay, so it's telling me how to process the packet after IP. If I said it was 17, then it tells me that the next header I should expect is the UDP header. Any questions on this? Yeah.
And that next header is inside of the same packet, right?
Right. So let me go back to, great question. Let me go back to that very first diagram. Where's that? Right. So if you remember going down the stack, we added all these headers. And then when you reached the destination, at the IP layer, you received a packet and you took off the IP header and the next header inside was TCP and you passed it up. So this is saying I'm going to take off the IP header and now do I know where to send? Should I send it to TCP or should I send it to UDP? That's what the protocol value is telling us. Any other questions? Okay. So finally, getting responses back to the source, we covered this already. I need the source IP address. So taking stock, these are the fields we're going to need in the IP header so far. We had two more tasks we needed to do. One was to deal with problems along the way, and the other was the specialized handling. What problems do you think we could have in the network? I think one of them came up, which was I could have some corruption. Some of my bits get corrupted by the equipment along the way. Yeah. Some packets could be dropped. Why? What could I put in the IP header, though, to help to deal with this packet will get dropped? It's not a bad thought, but... So if we had error messages, then it would make sense to have something like send an error for this packet. That's not what the standard IP does. It doesn't necessarily send, most of the time doesn't send error messages, yeah.
Sequence number of a bunch of packets.
Say more. Why would you need sequence numbers?
It's probably more useful in highlighters, but if you have multiple different packets and you chunk up your data into different packets, you're not guaranteed that all the packets will take the same route to the destination, and so you need to tell the endpoints how to piece back together in order the packets.
Okay, so you're right that we will eventually need some sequence numbers. We're going to do that at L4, not at L3, because the job of the network is not to guarantee that packets go in order, but we will need them when we get, you got to another point that we'll get to in a bit. So you need some signature, or we're going to call it a checksum, not so much for tampering, but just to make sure that the bits you sent are the bits you received, for whatever reason. Anything else? Right, you don't want the packet to wander the network. And why would the packet wander the network? Because, as you remember when we were talking about routing, it takes some time for routing to converge, and you can have loops while we're waiting for the paths to converge. And so if you didn't have any mechanism, these packets would just be looping forever. So we're going to have something we call a time to live, and we're going to drop a packet if it's been going around in the network for too long. Great, I think you guys got all the... fragmentation was the other one. So let's go through these: loops, corruption, and fragmentation. So preventing loops, as I said, while we're waiting for routing to converge, it's possible that you have loops for a period of time. We don't want packets looping forever in the network. And so very simple solution, we put a time to live in the packet header field. At every hop, as the packet is being forwarded, we decrement the TTL. If the TTL ever hits 0, this is one time we could send an error message back to the source saying time exceeded. And you used this capability when you did traceroute.
In the project, we checked just like the current universal time. Is that not done because it's hard to standardize the same time in decrement?
Typically, you don't have synchronized clocks across routers, so you wouldn't do an actual time. There is work on clock synchronization, so maybe one day, but not yet.
How come we're sending a time message, back to the source, but not?
Right. So this is a little arbitrary. In this case, we send a message back to the host saying, hey, I dropped your packet, time exceeded. And routers don't always do that for security concerns, but it's true that in this case we designed to have error messages, but in other cases we don't. A little arbitrary. I don't think I have a good reason for that. Any other questions? Okay, so just one point to note, if you want to send an error message back to the source, this is another reason why we need the source address and why routers need the source address. Okay. Header corruption, are people comfortable with the idea that bits can get corrupted along the way? Right. This comes down to, your signal at some level is an analog signal. And you look at the power or you look at some signal strength and you decide whether it's a bit 1 or 0. And sometimes if your laser flickered or something, a 0 could get flipped to a 1. And so there's physical characteristics of a link. There are reasons why you could corrupt bits or corrupt packets. So a checksum is just a compact fingerprint, or you can think of it as a hash, or there are lots of checksum algorithms out there that will summarize what the data being carried is. IP uses a particular form of checksum. The part 2 members, IP computes that checksum only over the IP header. Okay? And so if it's not correct, so every time a packet comes in, the router or the destination is going to check. It's going to compute the checksum over the header. It's going to compare it to the stored value of the checksum. If the two are not the same, it's just going to drop the packet. This means the checksum is updated at every router. This is a bit of a pain because it's a little expensive to compute a checksum. Why are we computing it at every router? Yeah. The TTL changed. Anytime I change any value in the header, I have to recompute the checksum. Why did we include the TTL in the header, in the checksum calculation? Why didn't we just say, I'm not going to include the TTL? Yeah, to protect the TTL, but not the best reason. A reasonable design could have been to say I'm going to leave out the TTL, but that's not what the earlier designers did. Why do we only compute checksums over the header? Because other bits could be corrupted as well.
It's not your problem at that layer, like you don't care
Yeah.
what the content is, and let a layer handle that.
Yeah, so the early designers were like, the job of the network layer, it's a very purist thinking. L3 is to protect the L3 header. I'm only computing checksums over the L3 header. Why did we even need a checksum in the first place? Why did routers, sorry, let me rephrase that. Why do routers have to check whether the packet is corrupted? What would happen if they didn't? Yeah? Yeah, so exactly that. The thinking was, well, what if I have a link that starts malfunctioning? Let me roll that back. What if a router did not check the checksum? What would happen? It would forward the packet on to the destination. The packet would reach the destination. The destination could check whether the packet is correct, whether the checksum is correct. And if it's not correct, it can drop the packet. So you should think about this, start thinking about the end-to-end principle. From a point of view of strictly correctness, it would have been fine to have not had routers compute checksums. Would have been good, in fact, a little less work for routers to do. And the end host could have checked whether the checksum was fine. You would have saved the destination from receiving bad data. So it would have worked fine. The thought was, well, we've wasted all this bandwidth for sending corrupted data over the network. This is slightly, people don't worry about it as much anymore because they're more worried about scaling routers than they are about checksums. And so we'll get back to that. This is a decision the IPv4 designers made that was maybe not ideal. Last point on the problems. One of the things that can happen is this question of fragmentation. I think this has come up in earlier lectures where we said every link has a maximum transmission unit. This is the largest unit of data that that link can carry. So sometimes a source might send a packet that is larger than some link's MTU. And so when the packet reaches that link, it is the job of the router at the front of that link to do what we call fragmentation, which is to take that packet and chunk it up into smaller packets. Okay, so if you had a large packet here, and let's say I was chunking it up into 1500, which is the typical Ethernet MTU, you would take that packet contents and chunk it up, in this case, into 3 independent packets, and you would create a new header for each of those fragments. And then ultimately you would have to reassemble those fragments back into an original packet. So it's conceptually it's a fairly easy thing to understand. Packet came in too large, I'm going to chunk it up and send out fragments, and then I'm going to reassemble it. It gets a little tricky and a little fun in exactly how you design fragmentation. So you're going to do this in section. Okay. Any questions on fragmentation, though, conceptually? Okay, so with that, we have added 3 more types of fields to our IP header. We have a TTL, the source address we already had, and we're going to have a set of fields to do fragmentation. There's a question somewhere that I... Yeah?
I have a question about each checksum. Wouldn't it also be beneficial because the destination source might have been corrupted, so you don't want to send it to the wrong destination?
Right. So what would happen if you sent it to the... That's a good question. If your destination bits were corrupted, but they still got you to some valid destination, would that destination accept it? Yes, you're right. That could be a problem. You'd have to have many things that go wrong, because you would also have to have a process, an application with a port, and that's sitting there. So, but in principle, yes, you could imagine that bad case. So the last thing in our header was this question of what if your packet wants some kind of special treatment? And there's 2 kinds of special treatment that the early designers of the internet considered. As you'll see, these fields have not worked out so well. But the first is, imagine that you don't want to treat all packets the same. You want to indicate some customers that are more important, higher priority, or traffic that is sensitive to delay or sensitive to throughput and so on. If you go back to our very first lectures, this was this idea that the internet should do more than just best effort traffic delivery. And then the second was the thought that maybe sometimes you want to do some kind of special functions or features treatment for the packet, like for diagnostics or debugging or other reasons. And so there was this entire class of fields called options that got introduced. Okay, so let's take the first of those. Type of service is exactly what it sounds like. It was originally designed to be a set of bits that would tell a router how to treat this packet. What kind of service does this packet want? Either, delay sensitive, throughput sensitive. Over the years, many people defined it and redefined it and tried to use it. It never really took off. The one use of these bits that has persisted is just for priorities. If you want to indicate different levels of priority, then this is what these bits are used for. And so today, finally, where these bits are a bit the laughing stock of the protocol designers because they have changed continually. But as of now, and for quite a few years now, they've been stable at this definition, which is you have 6 bits that we call DSCP, which is basically priority bits. These are used to indicate priority. And then you have 2 bits that are used by a router to indicate to end hosts whether they've experienced congestion. So we call those ECN. Don't worry about ECN for now. We'll cover ECN when we get to congestion control. Okay, so remember the primarily indications of priority. And then the last bit is this idea of options. So here the thought was, what if my router needs to do more than just forward a packet? And so there were examples of things people thought that would be useful to do. One is, for example, this idea of recorder route. What if you want to trace the path a packet has taken? I want to be able to tell a router you need to record your ID or record the path as this packet is traveling. Or if you wanted timestamps for diagnostics or debugging reasons, you want the router to put a timestamp so you know at what time this packet arrived at this router. Third option that was common was this idea of source routing. What if I want to tell the routers, here's exactly the path I want you to follow, overriding what your routing algorithms told you. So the thought was, you might have these more complex features or more advanced features, and the host should be able to tell routers what those features are. So this is why people designed IP options, again, not very widely used. Part of the issue with IP options, one was the minute you said, I have a whole set of optional fields, your header length is no longer fixed. Right? Your header length varies. And as you try to build hardware routers that process packets at very high speed, having to deal with variable length headers is complicated because the first thing you have to do is parse exactly what all these bytes are. So it's harder to have a parallel implementation, which is what allows hardware to go fast. And the second problem is many of these options, processing options, is an additional processing overhead on the router. And so they became ways of attacking a router. That if you want to attack a router, you send packets with lots of options set, and now you're exhausting resources at the router. So again, options kind of mixed luck in terms of how they get used on the internet. So, but two fields that you will see in your IPv4 header for that reason are these type of service bits and option bits. I'm going to very quickly just flash the IP header here at you because we've covered it. So we show the IP header, it's aligned on 32-bit boundaries, so 4 bytes. Fields you'd expect to see in the IP header for parsing, you have a version number, you have a header length, and a total length in bytes. The header length is counted in multiples of 32 bits, so in multiples of 4 bytes. We have the destination IP address, we have the protocol field, which tells us whether it's TCP or UDP or something else. We have the source IP address. We have the TTL and the checksum, it's 16 bits. And then we have a bunch of fragmentation bits that you'll design in section. And lastly, we have the type of service and some options. Okay, so if you go pick any IPv4 packet off of the internet and you look at it, this is what you'd expect. This is what you have to see. This is the protocol standard. Any questions? Okay, so just next time, which is not Thursday, but the lecture after that, we'll wrap up IPv4 to IPv6, what were the main changes in what we discussed, and then just a few security implications of the IPv4 header. Okay. With that, thank you.